Okay, it's time. So the announcement this week are essentially more quizzes, and PA number 6 will be doing. Okay. So good news is that there are only 3 quizzes during this week. Well, but for some of you, you might be a little bit anxious now because you're seeing keyword exam 2 grades. Okay. So the TA will be releasing the grades. You probably have already received the email. Okay. Now, just something that I would like you to know is this. Okay, the exam grades will be shifted, okay, by a constant so that the averages of all 4 exams are equal. Okay, so this is to compensate and normalize because the exams are going longer and longer. Okay. So some of these excessive lengths, okay, are probably not doable, okay, and it really depends on the length of each exam. So in some cases, the average could be actually lower, so we'll be shifting it high so that we normalize all the exam average at the same level. And this is necessary because we want you to be able to select 3 out of 4, okay, in a reasonable way. Because if there's one exam that's super long, right, then the absolute grade will be lower than all the other exams, and that doesn't make sense, okay, if you do relatively well in that exam. All right. Once again, the grade distribution is a perfect normal distribution. So that is also saying some of you did very, very well, exceptionally well. Okay. But more of you are doing much better than last time. That's why we see the standard deviation. Okay. Exam number 1 was 13, but this time it's lowered to 10.27. Okay. So this is a good sign that you guys are catching up with the exam style. So let me just ask quickly, did you guys receive the grades for exam 2? No, okay, so TA is probably busy shifting the average. So Caleb is a little bit careful. I'm guessing that he wants to, record all the grades to the grade sheet and make sure everything is right before sending you guys the emails, okay? Now, this week, we'll be doing a lot more reliable data transfer. But first, to cover the pipeline, the reliable transfer protocol. And then we'll move on to TCP dumps reliable transfer protocol. So let me play the slide. So this is where we're off, okay? We were doing, so 1 second. So we started talking about the performance issue of a RDT, particularly RDT 3.0. That's why we are brought to pipeline protocol. Because if we are allowed to send multiple packets in flight, like this plot on the right, you see that within 1 round trip time, the utilizations of the sender's transmission time will be a lot better. Okay. Now, there are 2 generic forms of doing reliable data transfer in the pipeline fashion. One is called the go back N. The other, selective repeat. In the next slide, I'm going to give you an overview of the 2 mechanisms. Okay, so you see that go back N on the left and selective repeat on the right. You see that there are 3 bullets for each protocol. So you also see, right, the first one, you see the same thing. Essentially, the sender will be able to send up to n UNAC packet. So n here, UNAC packet through the pipeline. So this is the same for both because both of them are pipeline protocols. But 2 protocols begin to differ from here. What the acknowledgement means. In RDT 3.0, we send data. Receiver there sends back acknowledgement. Okay, data packet, acknowledgement packet. So in RDT 3.0, the acknowledgement packet is for each individual data packet. But in pipeline protocol, it really depends on the flavor. Selective repeat is the one that's a little bit more like RDT 3.0, where you see the ACK carries a sequence number. And each ACK acknowledges each of the data packet we send. Okay, so the ACK is individual. But for go back in, the ACK is different. It's a cumulative ACK, look left. So in that ACK packet, it carries a sequence number. That sequence number actually means that the receiver is saying all the data packet all the way up to that sequence numbers are acknowledged. So it's cumulative. It's at once acknowledging many data packets arriving in order, in sequence. But then you can imagine, right? On the other hand, if the data arrives in sequence for a while, but suddenly there's a gap, the receiver there receives 1, 2, 3, and then 5. Receiver there does not send back an acknowledgement for packet 5. No. If the implementation of go backend is such that every time it receives something, it sends back an acknowledgement, receiving packet 5 there means the receiver of go backend will need to send back an ACK, but that ACK packet can only carry sequence number 3, okay, because it's cumulative. If it sends 5, that means packet 4 is also acknowledged. Okay. So that is what a cumulative ACK means. The third component is timer in RDT. Very important. How RDT 3.0 differs from version 2. something. The major difference is it carries a timer, because in case there's packet loss, we need a timer for the sender to discover, oh, it's necessary to retransmit. Okay. But the way the sender handles timeout will be different. So sender here for go backend has a timer. But that timer is only associated with the oldest packeting flight. So in pipeline RDT, we send multiple packets in one round trip. But in go backend, there's only one timer for the entire set of these packets we send out in one round trip time. But in selective repeat, more intuitive, there'll be an individual timer for each data packet sent. Okay. So there's going to be one timer for each unACK packet. Therefore, when timeout occurred, selective repeat, you can imagine, straightforward, right? If the timer for packet 3 expires, then retransmit packet 3. But then go back in. If a timer expires, what it does is this. It actually retransmits all the unACK packet in the flight, within the pipeline. So that is also saying that timer is actually for the entire flight, not individual packet. Okay? Therefore, when the timer expires, retransmit the entire flight. So let me summarize the overview. This part of the mechanism, the same. Okay? We would allow an unACKed packet. But the ACKs mean different things. Okay? ACK carrying a sequence number, for selective repeat, it's an individual. But for go backend, cumulative. Timer, for selective repeat, again, individual. But for go backend, it's for the entire flight. So you can imagine, okay, or you can try to think of go backend this way. Go backend tries to handle the group of data within round trip time at the time. But for selective repeat, it tries to handle all the packets individually, okay, within a round trip time at the time. Good. Now let's focus more on each of the mechanism. First is go back in. Now, the first thing we talk about is this. We now allow n unACK packets in flight. Of course, then, that n there is actually called with a special term called window. So these pipelined RDT will have a window, a sending window at the sender side. How many packets are allowed to go out without acknowledgement is limited by the window. That is also depicted in this example here below. So each small rectangle is a packet. Okay? And it's actually older packet on the left, newer packet on the right. So all these green packets are what? All packets that this sender have already sent, and the sender has already received the acknowledgements for. So the green packets are the packets already acknowledged. Okay, those are the packets we're done sending. And then there are these yellow packets. So these yellow packets are what? Packets the sender sent, but not yet acknowledged. So this is also the beginning of the window, the sending window. Now, sending window being n, that means at any round trip time, we allow n packets to go out, being sent without being acknowledged. But sometimes the applications do not have that many data to send. In that case, we could have some of the packets in window n being sent without acknowledgement. But because there's not much data to send, so there'll be some slots here that the sender are allowed to send, but no need to send. So these blue ones are what? The usable slots, but not yet used. Okay, so no packets are being sent. So to indicate the beginning of the yellow packet, we use another variable, send base. Right, that's the base of the window. Okay, the base of the sending window. But later on, you might see me using a variable that's simply base, okay, without the send or without the sending. Okay, so they meant the same thing, the beginning of the window. The first available packet that we could use to send additional data is going to be denoted using another variable, next seq num, next available sequence number. Okay. And so you can imagine the blank packets towards right. Those are the slots that are not usable. Okay. Good. And now we just need to recall the mechanism. ACKs are for the entire flight of packet. Okay, so each ACK will come with the sequence number. That's the n here in the ACK. But that n means all the packets before n have arrived at the receiver. So the sender can clear those packets and then slide the window over. Okay. So if this sender here receives acknowledgement for the first yellow packet, the first yellow packet will turn green, and the window will slide over one packet. Send base will move one more slot. Okay. Next sequence number, would it change? No. Next sequence number depends on whether there's more data coming from the application layer. Okay. And then I'm repeating myself. The timer for the oldest in-flight unACK packet. So if there's a timer times out, starting from the base, okay, all the yellow packets will be retransmitted. So that's when a timeout event occurred, retransmit packet from n all the way to the highest sequence number that has already been sent. So the timer there has also a number associated with it. Okay, that is also the packet sequence number, but that is the same base. Okay. Should be relatively easy. Now this is the finite state machine of go back against sender. So let's start from the transition that is the easiest, okay, that must happen at some point. This is what? Getting a call from above, right? Getting this RDT send call from the application. What the sender needs to do is to try to see, right, if there's slot available in the window. How do we know? We check, right? The next sequence number, is it within the base plus n? If it is, then it's within the window. That's great. Then we will be able to send data. Okay. So we call main packet. Excuse my voice. So you guys were busy taking midterm exams last week. I was busy talking over the internet, hosting a conference. So in case you're wondering how come, right? I didn't talk all that much, should be, but still running out of voice. All right, so let's generate that data packet. So in that packet, we carry the sequence number. We carry also the checksum. So we call the underlying unreliable channel to send it out. And then we do this. There's an if condition. That's new. It's checking whether base equals next sequence number. What is this for? That means this packet we're sending out, the sequence number happens to be the base. And have we talked about the timer? The timer is associated with the base. So whenever we are sending a base packet there, we start that timer. If we're sending a packet that is not the base, there's no need of starting a timer. Okay, the timer has already been started. And then we increment the send sequence number, the next sequence number. Well, on the other hand, okay, if the next sequence number is greater than base plus n, that means the window is completely exhausted. Okay, there's already something being sent, okay, and waiting for X. So this data request coming from the application will be rejected. Okay, so this data will not be changed into a segment and sent out. Okay. So that was the first transition. Okay, sender might get called from above. Now the second transition that we must also observe is this one here. So this is the case when everything is okay, acknowledgement comes back, okay, and acknowledging the packets that we send. So this is receiving a packet. Okay. And we check, it's not corrupted. So we first get the sequence number out of the acknowledgement packet. At the sender side, if sender receive a packet, it must be an acknowledgement packet. So let's extract the sequence number out of the packet and send it to base. What does that sequence number mean in the acknowledgement coming back? That is the receiver saying that all the way up to the sequence number, every packet is fine. That means the base should equal that sequence number. Okay. Now, if the base equals the next seq num, what does that mean? That means, all the yellow packets are gone. So in that case, we need to what? Stop the timer, because we had a timer started off for the base. Okay, because this acknowledgement is so powerful, it acknowledges all the packets. So the beginning of the beginning of the window, the send base, is exactly the beginning of the blue. That means there's no yellow at all. All the packets in the window are blue. Okay, so we need to stop the timer. If the send base does not equal the next sequence number, that means that flight is not quite yet acknowledged entirely. Okay, so there could be more acknowledgements coming back. Okay, in that case, that's not stop the timer, and yet we restart the timer. So let's wait for more acts to come back. Okay, that's not timeout and retransmit. Okay, they're just on the way. Let's refresh the timer a little bit and wait a little bit longer. Now this transition on the left, okay, this is just like RDT 3.0, right? If we receive a packet and the packet is corrupted, we ignored it. Okay. If the packet is corrupted, we'll ignore it and then wait until there's timeout. So the last transition is timer timing out. What does go back and sender do? When there's a timeout at go back in, we retransmit from the base and we retransmit the entire flight. So we're going to retransmit packet from base all the way to the number before the next seek num. Okay. So that's it. The sender side of the finite state machine of go back in. Receiver side, it's slightly complicated, but not that much. Okay. Let's look at the transition that is the most critical, which is this one on the right. Receiver here receiving a packet, and it's checking whether it's corrupted. Not corrupt, great. Is it carrying the sequence number the receiver is expecting? If it is, then this is a new data. Then the receiver would extract data out of the packet, deliver the data to the application layer, send back acknowledgement. So this acknowledgement is going to carry the sequence number indicating that all the packets in sequence up to that point, okay, all acknowledged. So ACK will go out, and then the receiver will be expecting the next packet. All right? So instead of like RDT 3.0, we have like a set of states for packet sequence number 0, another state, packet sequence number 1. We kind of all merge them together, okay? And just using the sequence number there to tell them apart. Now the other transition is this. If the data comes in, okay, somehow corrupted, or somehow the sequence number is not expected, receiver simply what? Send duplicate acknowledgement. That means the data is bad, or it's a retransmission of the data that I have received previously. It must be because of the ACK I sent earlier somehow got corrupted or lost. So receiver here simply retransmit the ACK that has been generated earlier. So this will be a duplicate ACK. When the sender receives this ACK, what does it do? It does nothing. Okay, so therefore a timeout would occur, okay, in case no more new acknowledgements coming back. All right, to sum up, you see, at the receiver side, if the data is corrupted or out of order, okay, that packet will be discarded. So there's no extraction of data, delivery of data. Okay, no extraction of data here, no delivery of data here. Okay. And we simply re-ACK the data packet, indicating what is the highest packet sequence number we have already received in order. So go back in. How do you like it? It's a little bit weird, isn't it? Right? It's pretty odd. But in the meantime, very simple. So acknowledgement is only handling the in-order sequence. Okay, so that is also saying, go back in here does not want to bother, okay, dealing with gaps, okay, of packets coming in. So here's an example, and the only example of go back in. So what you're seeing here, on the left is the sequence number, okay, and the window correspondingly. So the sequence number space goes from 0 all the way to 8, and the window size is 4. So at the beginning, we may send packet 0, 1, 2, 3 in one flight. And this is what you're seeing, okay, in the sender-receiver transmission diagram here. Sender here sends packet 0 first, and then, because this is pipeline, so packet 1, packet 2, packet 3 will all go out in one pipeline. So in this scenario, packet 0 will arrive at the receiver. So receiver simply check, oh, not corrupted. Okay, it's the number I'm expecting, therefore send ACK0. Similarly, receiving packet 1 sends ACK1. Well, packet 2 get lost in this scenario. Receiver won't be seeing anything, except that later it receives packet 3. How does receiver handle out of order packet? Well, discard, right? And send the duplicate acknowledgement. Send an acknowledgement that we have already generated earlier. Okay, so ACK1 here is going to be a duplicate. And it's going to go out and come back to the sender. Now let's move back to the sender side and see how the sender will react receiving these ACKs. Sender here will receive ACK0 first. So which transition the sender will trigger? The bottom transition, isn't it? It's not corrupted and it's a fresh ACK. So we'll set the base to the next value, okay? And then send packet 4 because we have just shift the send base 1 over, and now we can send packet 4. Similarly, upon receiving ACK1, okay, this packet is acknowledged. So 1 here is acknowledged, ACK1, this is acknowledged. And therefore, window gets slided over and we send packet 5. Packet 4 and 5 will come over and arriving at the receiver. But receiver see 4 and 5 both are not really in sequence, right? Because receiver is still waiting for 2. So these will be discarded. More ACK1 will be sent, just like when it's receiving packet 3. Now the ACK being generated upon receiving packet 3, that is an ACK1, okay? It's going to arrive here. Okay, but the thing is that the sender side actually ignores duplicate ACK, do nothing. So in the end, timer is going to time out. Okay, packet 2 is going to be retransmitted. And because the timer is associated with the entire fly at the time, so packet 2, 3, 4, 5 will all be retransmitted like this. But this time, 2 arrives at the receiver. So 2 will be acknowledged, and then 3, 4, 5. Are we okay? Should be. The other one, selective repeat. This one is a lot more intuitive. So you get 1 acknowledgement. The sequence number is acknowledging exactly the data packet. You get 1 timer for each packet. When the timer times out, you retransmit exactly data packet with that sequence number. Okay, so keyword, individually acknowledged and individually retransmit the unacked packet. Okay, so there's a timer individually for each unacked packet. But this sending window and the receiver size receiving window will look a little bit different. You begin to see green rectangles interleaving with interleaving with the yellow packets. Because now the ACK individually acknowledges the yellow packets. So this is what you see. Packet number 3 in the window gets acknowledged. Number 4 gets acknowledged. And then 6 and 7 also get acknowledged. So in go backend, you have yellow and blue only inside the window. But this time, you get green as well. Okay. What's a little bit interesting is at the receiver side. Receiver has a window of n as well, and it slides as well. Whenever the packet is received, acknowledges send. Okay, so there's a receive base here. So this is the packet the receiver is expecting, but not yet received. Okay. This is the earliest packet that the receiver is expecting but not yet received. In the receiver's window size, okay, you will see also these ping packets. So ping packets are data packet arriving fine. Okay, acknowledgements also sent. Okay, it's just that they are out of order. So this is saying these. Okay, so this the sender window corresponds to the receiver window. You see these 1, 2, 3, 4, these 4 packets, okay, before the receive base. These are all received and acknowledged. But for some reason, packet 3 and 4, acknowledgement received at the sender. But packet 1 and 2 somehow missing, corrupted. So sender there not acknowledging those 2 packets. That's why you see at the sender window size, these 2 remain yellow and these 2 green. Okay, so sender receiver, the window might be a little bit inconsistent. Receiver might go a little bit faster than the sender, because the ACK packets could be lost. All right. So this is to sum up, selective repeat. And what I'm trying to show here is instead of using the finite state machine, so I'm actually typing it up in English. The sender is on the left. Receiver's finite state machine is on the right. If you recall, go back and sender's finite state machine. They're just what? 4 transitions. So what I'm showing here is sender has 3 transitions. First transition is when there's data from above. Second transition, timeout. Third transition, receiving an ACK. Okay. And you'll see that the selective repeat sender is very straightforward. Okay, when there's data, send the next sequence, send the data with the next available sequence number. Timeout, check the sequence number on the timeout. If it's N, retransmit packet N. Receiving an acknowledgement, check the sequence number N there, okay, and mark that packet green, received. The only condition that is a little bit special is just this. If N is the smallest of all the unACK packet, then what? We slide the window over. Okay. This will allow the sender to send more packets. So it can happen also in the selective repeat. When the sender receives a particular ACK, suddenly the gap is filled. There could be already several green packets in the same window. Okay, so all you receive is filling in a yellow gap, and then everything gets acknowledged. Then the window size can slide really fast altogether to the first yellow in line. Receivers simply do this. Okay, so there are 2 conditions or 2 transitions. Well, actually, to be more precise, 3 transitions. First is if the packet received, so packet N here, is within the receive window. So this is one of the packets that the receiver is expecting. Okay, then send back acknowledgement for that packet. If it's out of order, buffer these packets that's arriving out of order. Okay. If it's in order packet, extract data, deliver the data all the way to the highest received in sequence to the application. All right. So slight complication is just whether the data packet is out of order or somehow fill a gap. If it fills a gap, then that's shift all the way. Shift also the receive window all the way to the next packet that's expecting, not yet received. Oh, this is a little bit special. If the N there is not within the receive window, what does that mean? What does that mean? Duplicate? How come? So data has already arrived. right? So receiving ACK N, and N somehow is outside of the receive window, before the receive window. What does that mean? Samuel was saying, hey, this is a duplicate data. Receiver has already received it before. How come the receiver received a duplicate data? Sender side finally times out, okay? Because the ACK going back could be dropped. So the sender side finally times out and retransmit. Okay. So this could happen. Okay. If N is before receive, you can still receive ACKs, but that's just ignore it. Don't extract data and pass it up, otherwise it will be duplicate. All the other cases, just ignore. Okay, do nothing. So here's an example of selective repeat. It's the same scenario we see for go back in. So packet 2 here is lost. You see here, receiver receiving packet 0 sends ACK 0. Receiving packet 1 sends ACK 1. Not receiving packet 2, but receiving packet 3. This is out of sequence, so we buffer packet 3. Do not extract data, pass it up to the application yet. Okay, let's wait, okay, for packet 2 before we do that. But we need to send ACK for packet 3, because ACK is individual in selective repeat. So ACK 0 here arriving at the sender. Okay, this is going to trigger this sender's window to slide over by 1. Therefore, sender is allowed to send packet 4. And packet 5 triggered by receiving ACK 1. Packet 4 will be buffer, out of order again. ACK for 4 will be sent. Packet 5 buffer, ACK 5 send. Now, after a while, the timer for packet 2 here, who got lost, will finally time out. And packet 2 being retransmitted. At this point, receiver sees, oh, finally, I fill the gap. And I can now slide all the way from packet 2 to packet 5. Okay? And the next sequence number it's expecting to receive will be packet 6. Okay. Now for all these acknowledgements coming back individually, okay, packet ACK 3, ACK 4, and ACK 5, sender will just turn those yellow packets to green, and that's it, record. This packet is acknowledged. That packet is also acknowledged. Okay. So you know that packet 3 and 4 and 5 are acknowledged, but the window size cannot slide. Because 2 is still missing. 2 is not yet acknowledged. So 3, 4, 5, although already acknowledged, the sender there of selective repeat cannot send packet 5, cannot send packet 6, 7, 8. Okay, although the window says you can send four packets. Okay, but selective repeat gives you this issue. It doesn't allow you to slide over anyway. All right, so the last point is actually more this. Let's try to derive the relationship between window size and sequence number. I think I actually mentioned this last week. Okay. Provided a window size limiting the number of packets we can allow in flight, each packet will carry a sequence number. Okay. What should be the proper sequence number range there? Okay. If the window size is 4, should the sequence number range being 4? You need at least 4, right? So that you can distinguish packets within the window. But do you need more? Well, let's take a look at an example here to see if it inspires you, okay, to know a little bit better the relationship between window size and the sequence number range. So this is a scenario. Let's assume the sequence number range is only 4. 0, 1, 2, 3. The window size is 3. That means we can send 3 packets in flight without being acknowledged. Now, it takes us to this scenario. Sender on the left, receiver on the right. Sender there, given window size being 3, can send immediately 0, 2, 3. Packet 0, packet 1, 0, 1, 2. So packet 0, packet 1, and packet 2. So in this scenario, receiver gets all 3 packets fine. Therefore, acknowledgement for packet 0, packet 1, and packet 2 are all sent. And in this case, okay, when X0 arrives at the sender, we slide the window over and send packet 3. But packet 3 got lost. So receiver will not be receiving another packet 3. And then here, sender receiving ACK for packet 1. Then sender here now thought, oh, let's slide the window over and send the next packet, packet sequence number 0. And that 0 would arrive at the receiver. And it's going to check, right, the first transition, in fact, because it's within the within the receive base to the receive base plus n, the window size, minus 1. Okay, so it's going to think that, oh, it's a new packet, right? But is it going to extract data yet? No, right, because 3 is still missing. So 0 there will be buffer at the receiver. Okay. But receiver at this point is definitely thinking that packet 0 is a new packet. But hey, you see, 0 here is indeed a new packet, so no problem. Now, what about this case? Packet 0, 1, 2, send. ACK 0, 1, 2, send. But very unfortunately, all 3 ACKs are lost. In this case, we're going to have a timeout for packet 0 and packet 1 and packet 2. So let's start from the first timeout. What do we do there? The sender retransmits packet 0. Receiver is going to receive packet 0. And hey, packet 0 there is within receive base plus n minus 1. Therefore, receiver is going to say, okay, cool, this is a new packet. I'm just going to buffer it, okay, and not yet extract data and pass it up. Wait a minute. Look at this. This is what? A retransmission of this packet 0. It's not really a new packet. Ouch. Yeah. So now as human beings, you see, okay, the sender are actually sending different things. Okay. Now we see the senders are sending different things. In this case, it's a new data. In this case, it's a retransmission. But okay, if you are a computer and you are a receiver, okay, this end, you actually don't know. You're behind the curtain. You don't know what the sender situation is. Can you tell? Can you tell? Okay, whether the sender is in case 1 or case 2? As a receiver, you see, hey, I'm just getting packet 0, packet 1, packet 2, and then again, packet 0. And that's all. The 2 cases are identical. Receivers see no difference in the two scenarios. Okay. So in the second case, that retransmission of packet 0 is going to be treated like a new packet. Later on, after receiving 1 and 2, after receiving 3, in fact, it's going to extract 0 again and pass it up. You ended up having a duplicate. So what is the relationship, okay, between sequence number range and the window size? You know what? Yeah.
The sequence size times the round trip time to be larger than the timeout.
Larger than the time. Sequence number plus round trip time larger than time. Oh, that of course, because that is actually describing one of the case here. That is to prevent the acknowledgements being delayed for too long, right? That's one way of thinking about it, Jing. Gao Weiyao. Oh, sequence number range should be 2 times the window size, at least. Why?
So the windows will not get the same packet.
Okay, so let me try to rephrase. You see, Gao Weiyao observed this thing. The problem is this. 0 is within the receive window. So 0 is interpreted at the receiver side as a new packet, but it should not, because 0 can be dropped somewhere. So in this B here, this is like the worst case. 0 and 1 and 2 somehow can all be lost. Okay, so what receiver is expecting here should not have 0, 1, 2. Because they might need to be retransmitted, right? So all these sequence number in the green window there should not, okay, contain the packets still in flight. Okay. Still being acknowledged. Okay. So 0 should not be in the green part there. 0 should be outside of the green part later. So green part is a window, and the worst case, you can have the whole window of packets being lost. So one window there to allow all these packets being lost, and one window there, okay, not showing the same packet sequence number in the previous window. Therefore, 2 windows at least for the sequence number. Okay. So when there's a new 0, that needs to be received at the receiver side, it's going to be later, okay, outside of the green part. Good. Great. So this is actually a perfect time to take a break. But before the break, okay, let me introduce. This is just a summary. Okay, it's the same slide that I have already provided in the overview. Okay, the quiz. So feel free to use the time during the break to think about this. So this is quiz number 18. Great. So there are, questions coming. Very good. Let's see. So quiz 18 here is asking you to spend some time to do more contrast, compare and contrast of the two protocols. Q1 is asking, which method tends to use more network bandwidth to retransmit in case there are losses? Which one? Q2, which one of these tends to require more memory space at the receiver end? Q3, which method tends to require more timers at the sender end? Q4, this one is a little bit more open. The answer could be a little bit subjective. If you will be implementing a pipeline reliable transfer protocol, and your goal is minimum effort, okay, is it go backend or SR you would choose to implement? All right, so with that, we take a break for 10 minutes. Okay, find your teammate and discuss. And Jingyan, I see the two questions. What is the use of next sequence number in selective repeat? Okay, so this is concerning the finite state machine of the selective repeat, which I just use English instead of using the finite state machine. So I will try to explain after we come back from the break. The smaller the window size is, the more likely duplicate data being recognized as a new. Yes, yes. Okay, so for that question, it's very simple. Yes. Okay, the smaller the sequence number. Okay, duplicate. Well, actually, the smaller the sequence number range, okay, the easier duplicate data being recognized as a data, as a new data. Okay, so Jingyuan, you think about it. Okay, it should be the other way around. Okay, let me know if it's more clear. Okay. Good, Jingyuan, I finally see your response. It's okay.
Excuse me, can
Sure.
what does it mean base equals to next sequence number?
Oh, okay. So base is the same base.
Yes.
Okay, and base is pointing to the first packet in the window.
Yes.
So if this value equals this value, this means this packet we are sending out is the first yellow.
And what would happen if I see here next sequence number when next sequence number is more than the base
Plus
plus
n.
n, so it will plus 1.
Yeah.
So the next sequence number will move to here,
Yeah,
and
yeah,
here,
yeah.
and here, and here, and here.
Yeah,
and,
yeah, yeah.
What would happen next?
Oh, okay. So if next sequence number is equal base plus n or larger, that means all these packets are yellow.
Yes.
So can you scroll up a
Okay.
little bit? Yeah, we'll refuse data. So we tell the application layer that no, we cannot send data. There's no more space.
Then how would the window slide over?
The window will stay there.
Then why here the window will slide over?
Oh, okay, because the window slides over when it receives an acknowledgement. So acknowledgement received, this 0 here was originally yellow. Now it turns green.
Okay.
And so we slide the sending window over because we can send 4.
Yes.
So this is
So this is not described in this figure.
No.
Then
Well, actually, that is described, but it's implicit here. So we get the base. Okay, if base equals next sequence number, stop timer. Otherwise, restart timer.
but now we're at here, right?
No, sender is like this, having the whole thing and all the packets being yellow. The next sequence number is actually pointing at the first blank.
Yes, but you will refuse to receive this, right?
Right.
Then I still don't
Okay.
really get it.
Okay, let's go back up
Oh,
here.
okay, sure.
Go back up here. Okay, because at this point, base is changed.
And what does it mean? Base equals to get egg number
Okay,
plus
so
1?
this is an acknowledgement packet, right?
Yes.
So we get the acknowledgement sequence number out of the acknowledgement packet.
And y plus 1.
That means the first yellow packet is the next one.
The first yellow packet is the next one.
The base is now shifted over because whatever this acknowledgement sequence number says, that packet is acknowledged.
So what will this function return? The gets egg number.
It just get the sequence number of the egg packet.
Also, this will let the base now point to this one.
And so if at this point there's data coming in, base is now here. So plus n. So this slot is allowed to send.
Oh, okay. Oh, okay, I see. And what does it mean if the n is the smallest egg number? And yes, what does this sentence mean?
Okay. So if n is the smallest n egg packet, advance the window base to the next n egg sequence number. So that means because smallest n egg, that is the first yellow packet, and this is selective repeat, right?
Yes.
In selective repeat, you could have yellow, green, yellow, green.
Yes.
If the egg we receive, okay, is the lowest, smallest, earliest yellow,
Oh, yeah. So
there.
base now will be here.
base will be to the next one.
Next one.
Yeah.
And the next base will be here, or
Yeah. If this one is acknowledged, the next base will be here to the next
Okay.
n egg sequence number.
okay. Okay. Thanks.
Okay. So let me just add a couple things. All right, so I guess you guys kind of figure out what base or same base mean. They are actually simply this, the first yellow packet. Next sequence number, the first blue packet. First yellow means that is the base of the window. So base will only change when we slide the window. That is also saying when the base is changed, that action itself slides the window. Okay, so when I was describing using the scenarios, I say, oh, okay, acknowledge, and then we slide the window over, we can send one more. That is because send base there is changed. Base is changed. So when we're sending, we check whether there's enough space. So send base plus n, okay, or send base. Whether the next sequence number is less than send base plus n minus 1, right? So when base is changed, then we have one more slot, and therefore we could send more packet. So in the sender's finite state for go back n, where is the window sliding? It's actually here, because this is where base is changed. Base equal get ack number. Okay, so the receive packet there is the acknowledgement packet. So get ack num there is a function that allows the system to give back the sequence number on the ack packet. And that is that. It's very simple. So essentially, the base is changed to that sequence number. So base is changed. That means the window slides over. When is window slided over? In selective repeat. So where is base changed in selective repeat? Where? Here, right? If n is the smallest unacked packet, advance the window base to the next unacked packet. So essentially, where is the window sliding going? In the transition where we receive a new acknowledgement, so we can change the base. So this is just so that you guys know a little bit better, when is sliding really happening? Okay. And also, so there's another question. So Jingyuan was asking, hey, is next sequence number used in selective repeat sender? In fact, it is. It's just that the finite state machine of selective repeat is actually given here in a fuzzier way. So I'm saying that I'm listing it and talking about it like it's English. Okay, so there are 3 cases. In case we get data from above, we just generate the next packet carrying the next sequence number. Okay, so next available sequence number is exactly next seq num. Okay. So feel free to let me know if there's any point being confusing. Okay. But from last week, you guys should know that it's more that you are not familiar with the state machine more than this is really hard to understand. Okay. Good, so let's move back to the quiz. So what do you think? Q1. Which one is going to consume more network bandwidth? I know that some of you guys have already go to the Slack and answer the question. Anyone wants to answer in class? Okay. Go back in. Why? Why do you think go back in consumes more bandwidth? A whole flight? Yeah. Okay. Is that right? Do you think so? Because every time there's a timeout, right? You will be retransmitting from the base all the way, right, to the next sequence numbers -1. And I think you are Xu Wei, Xu Wei. So what about Q2? Anyone would like to try Q2? Selective repeat. Selective repeat will require more memory space at the receiver end. Why? If it's out of order, right, you need to buffer it. What's your name? Jia Hong, I see. Team 5. Do you agree? Right, the go back in, receiver, if it's out of order, just discard. That's it. Right, so there's no need to store packets at the receiver for go back in, but selective repeat does, okay, store, buffer these packets. What about Q3? Which one requires more timers at the sender side? James and Howard?
I think selective repeat requires more.
Selective repeat requires more?
Yeah, because it requires individual timer for each.
For each packet, right? For each packeting flight. Is that what you were going to say, Howard?
Yeah.
Selective repeat. So this one seems quite easy because timer is individual for each packet in selective repeat. Q4, if you are going to implement an RDT, a pipeline RDT, would you take go back in or selective repeat? Howard?
I think I would take go back in because I don't need to remember the fault package or all the package. It's more easier for me to prepare the memory in the receiver side.
So Howard is saying go back in. Because at least for the receiver side, receiver doesn't need to buffer anything. Sender has only one timer, right? Times out, retransmit everything. It will work. So if the goal is to try to implement as soon as possible, go back in. Any other opinions? Different calls? No? Let's go to the Slack and see what are the other. Oh, right. Oh, okay, we see that go back in for first question. Selective repeat, more timers, more space. So selective repeat just need more space, right? Sender and receiver end. But go back and drawback consume more network bandwidth. Okay. So team 12 is saying let's do go back in, right? We do consume more bandwidth, but it's a lot more easier to implement. Hey, team 19. I see the same thing. It's easier to track just one group of packets instead of individual packets. Team 2. If the cost of buying memory is less than extending bandwidth, then we'll go with, okay, good. So you know the trade-off very well, right, between bandwidth and memory space. Team 1 here says go back in. Much easier to implement. Hongxuan? Okay. Oh, okay, that's just being added, okay. So team 8, very similarly. Okay, James was actually there speaking about A3, answer for Q3. Okay, so Angela here saying the same thing. You don't want to deal with allocating memory and buffering packets. That can be tedious, yeah. All right, so I see team 5 says the same thing. Team 10 also go back in. Boxun, team 4, very much the same, good. Oh, team 15, Kevin, Okay, Kevin right here, good. Go back in. It's easier to handle. So you don't have to allocate memory space and track, right, which packet arrived out of order and which one have already acknowledged. Good, so let's go back to the lecture. Oops, this is the quiz, not the lecture. So you know what? We're done with the pipelined protocols. And it's time, let's move on. So up to this point, what we've talked about are the general design principles of reliable data transfer protocols. How is reliable data transfer implemented in TCP? That is the question, right? So TCP, we know, is the protocol on the internet that does reliable data transfer. But is TCP go back N or selective repeat? Okay, we'll find out. But we'll see if we're lucky. We'll be able to find out today. If not, then on Thursday. Let's try to give an overview of TCP first. Okay, so some of these terms you've seen before, very straightforward. So first of all is point-to-point between a pair of sender and receiver. And it's sending data reliably and in order. Oh, okay, pipeline. So definitely either go back in or a selective repeat, okay, or somewhere in between. But the thing is that TCP not only handles reliable data transfer, but also these, congestion and flow control. Okay, so the sending of the data will be able to react to the traffic load or the receiver application load. So speaking of that, let's come here. Flow controlled, so this point here. Do you recall flow control? Flow control? Okay. So congestion control is so that TCP will slow sending data out instead of overwhelming the network. Okay. So overwhelming switches or routers inside the internet. Flow control is so that the sender slows down sending of data to not overwhelm just the receiver. Okay. If you recall, what is the benefit of using UDP? DNS use UDP. What else we mentioned would be nice to use UDP? Exactly. Who was saying? Are you, Samuel? Because I cannot see you guys' mouses moving. Okay. Live stream, video. Right? Video streams, high bandwidth. If we use TCP, it's going to be limited very much by the congestion control. So UDP is nice for large streams. But the thing with large stream is that, hey, if everyone is watching video, and videos are all sent through UDP, then some routers who are a little bit more centered to many of these transmissions could get congested. That router could be very busy, and we could be running out of buffer space. Okay. So in that case, UDP might not be very good, because that is the case. You're supposed to slow down from the sender, because otherwise, whatever you send, getting to the congestion point and packet get dropped. That is also why this weekend is the Labor Day weekend, right? It's somewhat long weekend. Your parents will probably not bother getting onto the freeway. Why? Freeway is going to get congested. So how does Taiwan's freeway control system handle congestion on the freeway? Yeah, there's ramp control, isn't it? When the cars are on the ramp going onto the freeway, there's a light, traffic light, controlling the speed of cars entering freeway. The more congested, the longer the red light is. Okay, so the longer the wait the cars getting onto the freeway system will wait. So this is the same thing. TCP does congestion control, slowing down because there are already too much traffic. Flow control is so that the receiver, the process is running on the receiver, could also take time. Well, if your laptop is lower end, then it will take more time. So some other processes will suffer. Okay, so in that case, receiver would also tell the sender to slow down using the flow control mechanism here. Okay. So flow control is so that receiver is not overwhelmed. Congestion control is so that the network does not get overwhelmed. Two other terms. Connection-oriented is also well known. We've talked about it before. Connection-oriented. So this is saying that TCP between the sender and receiver, before data can be exchanged, there'll be some control messages, handshake messages, okay, being sent back and forth. So those are important because the sender and the receiver side, there will be some variables we need to initialize. For example, sender might be sending data to the receiver. Receiver sending egg back. For receiver, it's very simple, right? By looking at the data, receiver knows what is the sequence number to be inserted into the egg. But hey, receiver also need to know, right, whether this data coming in is expected. If the sender is already sending some data over, receiver would just know, right? Increment to the next expected sequence number. But to begin with, what is the initial expected sequence number for the receiver? Well, for all the examples we see earlier, we kind of all start from 0. So it seems no-brainer. Receiver would just expect 0 to begin with. But would that be good? Think about this. What if you have lots of short connections? Okay. So you start 1, you send packet 0, 1, 2, 3, 4, 5. And receiver thought, oh, everything is collected, and that's closed the connection. But sender here missing some of the eggs, retransmitting 0, 1, 2, 3, 4, 5. Okay. But there could be another TCP connection coming up using the same port number to the receiver. It is also 0, 1, 2, 3, 4, 5. How do you distinguish the earlier 0, 1, 2, 3, 4, 5 from the previous sender to the 0, 1, 2, 3, 4, 5 from the next sender? In TCP, to avoid confusion like this, okay, if you always start from packet 0, you get that a lot. Because packets somehow get stuck in the internet. Routes can change, right? Recall chapter 1, routes can change. Packet gets stuck. Now they come back a little bit later. And sender here, timer times out, retransmit 0, 1, 2, 3, 4, 5. While the second sender sends 0, 1, 2, 3, 4, 5. It's a headache. Therefore, in TCP, the sequence number does not always start from 0. It actually goes incremented, 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 incremented for the same port. That sequence number could be different the next time you're starting it. So this is to avoid lots of short connections coming, dying about the same time. So the connection-oriented nature here, okay, is for the sender to tell the receiver, okay, this is the initial window size I'm going to starting. So receiver knows the first data coming in is going to carry that sequence number. Last notion. Okay, so this we also talked about briefly when we started talking about the RDT. So full duplex data. So when we started talking about reliable data transfer, we say, hey, that's developed finite state machine, isn't it? And for simplicity, we assume data travel only one way, from sender to receiver. But what really happens on the internet is this. In this TCP connection between sender-receiver, between client-server, data can go from client to server. Data can also go from server back to the client. Think HTTP. Client sends HTTP requests. Server there needs to send acknowledgement for these HTTP requests, data bits. In the meantime, server needs to also send HTTP reply. So there's also data going back. And the client here sends acknowledgement for these HTTP responses. So data can actually go both ways within the TCP connection. Okay. So data flows bidirectionally in the same connection. TCP packets, they are also limited in the maximum segment size. That is called the MSS. Usually what TCP does is to send to the maximum, okay, if the data volume is high. Okay. If there are more than the MSS bytes of data to send, then they will be divided into multiple packets. And what's in the packet? If you recall UDP, we talk about the packet format, isn't it? Most of the UDP packet is just data. Header, very straightforward. Source port number, destination port number. And then what? Packet size. And checksum. That's it. TCP, a lot more complicated. You see, however, very similar to UDP packet, there's source port number as well as destination port number. And checksum. So UDP does not do reliable data transfer, but it still tells whether the data is correctly received or not. It tells whether the data is corrupted. UDP is limited. It doesn't do reliable data transfer. But TCP, needing to do reliable data transfer, will definitely have the checksum. Now, what else do we have here in TCP's header? What are these? So there are these UAPRSF. So look at these, UAPRSF. So these are special flags, okay, you see in the TCP header. So A, if that flag is turned on, so if the value there is 1, it means this packet here is also an acknowledgement packet. That means you need to take this number here, acknowledgement number here, and use that to acknowledge data coming the other direction. Okay. So A indicates this is an acknowledgement packet. There are 3 more bits, R bits, S bits, and F bits. R stands for reset, RST. S stands for synchronization, syn packet. And fin is simply fin, that's Latin for the end. Reset, synchronization, fin. You can probably imagine already from the names of these. They are allowing establishment of the connection, reset of the connection, or closing of the connection. Okay, so syn there is for starting of the connection. Reset is to restart the connection. And fin here is to close the connection. There are 2 more bits there. So there are 6 in total. 2 more. P is the push bit. Okay, so this is actually telling the TCP receiver to quickly extract data and pass the whole data up to the application layer. but it's not used really in practice. Urgent, that means there's somewhere, inside the data somewhere, there's some data being very, very urgent. Okay. In that case, the urgent bit, U bit, will be set to 1. Now, this is not used all that much, okay, but it used to be used a lot for the telnet sessions. Okay. So sometimes in the middle of the telnet session, you might want to close the connection, and that close command might get an urgent bit. Okay. But that command might be somewhere in the middle of the data below. So this guy here, urgent data pointer, is to point out where in the data, where in the data is that urgent command, okay, the receiver needs to execute. Now, the only 3 fields that are new to you will be this, the window size, and sequence number, and the acknowledgement sequence number. Okay. So sequence number is exactly the data sequence number. Acknowledgement number is exactly the acknowledgement packet sequence number. Now, because data can go both direction, ACK can go both direction, you see that in a TCP packet, it could be a data carrying the ACK for data coming the other direction, you see. The receive window here is used by the flow control. So this is for the receiver to tell the sender what is the proper window size to use. So inside a packet header, for a SYN packet, okay, when the connection is established, or when the receiver is suddenly busy. So this receive window here might be carrying a number telling the sender to limit the window size, okay, to that number. So you see also, the window size of a TCP sender can change over time. Oh. Ouch. Good that I brought my umbrella. My office is in the other building. Did you bring your umbrella? No? Yes? Oh, ouch. Oh, well. It might go away, though. Okay. Well, let's come back here. Okay. Bidirection. Okay, so that's something that's a little bit new. Okay, to many of you, it's a little bit awkward. So you're still consuming that idea. So there's something else that you need to consume as well, which is quite different from what we've talked about, the RDT. In RDT, all these finite state machines, what we are assuming is we are counting the packets. Packet 0, ACK 0. Packet 1, ACK 1. So the sequence number is per packet. But in TCP, the sequence number is actually per byte. It's a very fine granularity. So each of these rectangles you see on the slide. Oopsie. So each of these rectangles you see on the slide is now what? A byte, not a packet. So what we're sending here using TCP is a byte stream. Okay. So the sequence number in a data packet will be the sequence number for the first byte of data. Okay, first byte of data, right here. And if one receives an acknowledgement packet, that sequence number in the acknowledgement field in the packet header indicates what is the next byte the receiver is expecting. Keyword here. TCP receiver sends acknowledgement as cumulative acknowledgements. However, TCP's receiver, okay, unlike go back and receiver, just discard packet, in TCP standard, it is not really specified clearly whether the receiver should just discard packet or buffer the packet. So the spec there, the standard there, does not specify. It's up to the programmer, okay, whether they want to also buffer packet, okay, to save some bandwidth, maybe. So if we focus on this plot on the right, this example on the right, so the green bytes are the bytes that have already been sent and acknowledged. Yellow bytes, the same, that have been sent already but not yet acknowledged. Blue ones are available to send but not yet used. The gray ones are just like the blank ones, not usable. Okay, so if the sender here wants to send data, the sequence number here in the packet header, so the red block here, there, will be the sequence number of the first blue byte. If this sender receives an acknowledgement packet coming, it will look at the acknowledgement number down here, again, the red bar. And if the acknowledgement number is indicating that it's the second byte, second yellow byte, that means the receiver is expecting the second yellow byte next. The receiver is acknowledging the first yellow byte received okay. Okay. So the first yellow byte here is going to be turned to green. Sorry, it's very hard to use the pointer. Okay, this guy is going to turn green, and the window size over by 1. So the base is going to be changed. So this is acknowledgement packet, you see, with the 8 bits on, down here. So really, TCP sends with sequence number indicating the bytes. In the data packet, sequence number is the first byte sequence number. In the acknowledgement packet, the sequence number is the next packet the receiver is expecting. That means 1 byte before that next sequence number it's expecting are acknowledged. So here's an example. Host A, host B. Host A here types up a character C, and that's only 1 byte. So host A here is only sending a data packet with 1 byte. So let's say that that C character there is in sequence number 42. Okay. And in the packet, we carry data, just 1 byte C. Well, this packet here is also acknowledging some packet coming from B to A. And that next sequence number A will be expecting is 79. So host A here receiving this packet, okay, acknowledging C is received, sends acknowledgement back. And in the meantime, it types also a C and send back to host A. So it's going to look like this. Sequence number here is the first byte, which is 79 because A is expecting 79 next. What is the acknowledgement number here for this packet? 42 is the first byte, and it's only 1 byte long, right? So B will be expecting next 43. So ACK 43 here. Sequence number 43, because there's no data going. And acknowledgement is for this packet coming over here, starting from 79, and it's only 1 byte long. So next packet, sequence number A is expecting to receive is 80. So this is a simple telnet scenario. B is the server, A is the host. So you connect to B, you type up a C on the terminal. B there will show a C on the terminal. Okay, and that showing of C needs to come back to you. Yeah, so C, C, and that's it. Okay, so the last one is essentially just to acknowledge receiving the C coming back from B. So it's not carrying data. So even though there's sequence number 43, but there's no data. So when B is sending an acknowledgement back, it will be sending ACK 43, still expecting 43. Well, that's exercise, okay? Counting sequence number in TCP. I know it's a little bit tricky. You guys had no idea what I was saying. And that's why we have quizzes. All right. So this is quiz 19, by counting. Yeah, figuring out the sequence number for TCP packets. So on the left, what you're seeing is host A and host B sending data, sending ACK. The data is only going one direction from A to B. So here, A only sending to B. So this is the data packet, this is the ACK packet, this is the data packet, this is the ACK packet. So the first packet starts from sequence 42. Data is 7 bytes long. Therefore, the ACK is 42 plus 7. The last byte sequence number is what? 48, isn't it? Therefore, the next byte, B is expecting 49. Next packet, therefore, starting from sequence 49. It's only 3 bytes long. The returning ACK carries sequence number 49 plus 3. Now, quiz 19 is asking you to try to fill the blank here for the scenario on the right. So this is the scenario where you have data going both directions. Things can go a little bit confusing. All right, let's see. A sends data starting from sequence number 42, and it's 10 bytes long. In the meantime, A is telling B that the next data bytes that A is expecting will be 79. So B here needs to return a packet. Purpose number 1, acknowledge this packet it just received. Purpose number 2, it's sending also something from B to A, okay, and starting from the sequence number, and it's 20 bytes long. So what should be the ACK sequence number here? So this is the easiest one, right? Because the packet, data packet coming from A starts from 42. 42 plus 10, yeah, 52. What is the sequence number here, A? Well, A says I'm expecting 79, so this must be 79. All right? Can some of you tell me what is C and what is D? What is D? I heard someone saying something. Okay, too easy.
I don't know. Is it A plus 20?
Is it A plus 20? It is, right? But what is A? Forgot. A is 79. So D is 99. Do we all agree? Yeah, I think, I'm guessing Chen Jiahong is trying to say the same thing, right? And I think you are Kevin. So this is quiz 19. What is C? What is the value of C? Zalde? 52? 52. Actually, I don't C, 52. How did you come up with that?
Same as B.
Ah, okay. C should actually reflect B, right? Because B is how host B is telling host, hey, what is the next byte to expect? And B we just derived already, which is 52. So C should be 52. So let me see. Where's Yuting here? Oh, Yiting. All right, Yiting. What about E and F? E and F? James?
E is the same as D, so it's 99.
Okay, okay. Because D there is a host, A telling host B what is expected next. Mhm. Okay, I agree. What about F? F? C plus 0, of course. Okay, and C was 52. Therefore, F is also 52. So let me write things down. And I believe you are team 1. Zhou Ziting. Okay, good. Okay? Still confusing? Okay, getting a little bit closer. Okay, so eating there, fill it in. Okay. All right, so that was quiz 19 because it can get really confusing. So these notions on the internet gets complicated because a lot of time it's a distributed system, okay? And they can go parallel running. In one direction data, and in the other direction the acknowledgement packets. Okay. Good. So finally, packet format, and what's a little bit unusual in TCP from the reliable data transfer mechanisms we've talked about. Okay. So you see that the RDTs, although already a little bit complicated, is still simple comparing to TCP. Okay, so this is done. And then segment format is done. Packet sequence number also done. Okay. So we'll be entering TCP's reliable data transfer. But before we start talking about in TCP how reliable data transfer works, TCP defines this thing. Because in RDT 3.0, go back in and selective repeat, we need to set up timers, right? For each of these timers needs to be a timeout interval. How do we decide the timeout interval? We've never talked about this, okay, in any of the RDTs we talked about earlier. So TCP, what it does first is to try to address this issue. What should be the appropriate value, okay, for the timeout? We know if it's too short, we get premature timeout. That's not good. There will be more bandwidth we consume. If it's too long, this TCP connection might be slow, okay, reacting to packet loss. What will be an appropriate timeout interval? Well, we know it needs to be longer than round-trip time, definitely. Right? If you set it shorter than round-trip time, then every ACK will be timed out. No way, right? Definitely longer than round-trip time. Great. Longer than round-trip time. All right? The challenge is this. Well, you wish that the round-trip time is a constant. It unfortunately isn't. In fact, let me bring up a measurement result. Okay? So someone tries to measure the round-trip time over a connection, and this is what you get. So the dark blue, okay, each of these indicates a sample of the round trip time. So what's being done here is that at the sender side, it tracks the time sending a data. It also tracks the time the acknowledgement for that data is received, right? Data go, trigger acknowledgement to come back. By subtracting the time of the data and ACK, you get the round trip time. And so you get, fluctuating round trip time estimates. That is why the timeout estimation mechanism in TCP is somewhat elaborated. Okay, it's not just, calculate the time difference and that's it. Okay, so how to estimate the round trip time? It's somewhat elaborated. Okay, first, calculate this, the sample RTT. So take the time the segment is transmitted until the acknowledgement is received. That is one sample RTT. Now, in some cases, data can go and ACK did not come back, so that the sender needs to retransmit. In that case, hey, do you subtract the first transmission's time or the second transmission's time? You get confused. So in case there's a retransmission happening, let's ignore that RTT sample. Okay. So we know sample RTT varies. Okay. So if we use the instantaneous sample RTT, it's really risky. Okay. So instead, you want to smooth the sample RTT and set it even higher such that most of the sample RTT is below that threshold. Okay. So you want to average several recent measurements, okay, and not just the current one, and include the variation of the sample RTT. So what I was describing is exactly the mechanism. So there are two parts, okay, in finally coming up with the timeout interval. First, estimate the average RTT. So this equation here is to just measure the estimated, the average RTT. Okay. And this is not the end of it. After you get the estimated RTT, you also want to make sure that the estimated RTT is added at safety margin, okay, so that all these sample RTTs is going to be below the threshold, below the timeout interval. So the timeout interval in the end will be the estimated RTT, which is the average of sample RTT, plus the estimated deviation of the RTT. And the deviation of RTT, or variation of the RTT, is estimated using this equation. Okay. Now, you guys are going, hey, Polly is talking too fast. Okay. Yeah, there's a reason, because we don't have time to go into the detail today. Thursday, okay, I'm going to go over the detail. Estimated RTT, it's actually the sum, and it's a weighted sum, okay, of the previous estimated RTT to the most recent sample RTT. You see here? Estimated RTT equals estimated RTT and sample RTT, and the weighted sum of it. So this equation is not your average math equation. Okay, because the usual math equation, this won't hold unless sample RTT equals 0. Okay, so this is, think of it as a program instruction. So you are setting the new estimated RTT as the sum of the previous value of estimated RTT to the sample RTT. Good, so we'll talk about this more on Thursday. Okay. All right, so let's go. Okay, all right, guys, I'm going to end the stream. There we go.